Hello everyone and welcome to the video. In this video we'll be talking about object programming. Now if you're like me and you first start learning functional programming, you basically want to throw out everything else you've learned in the past. And this is kind of a bias we have naturally, I think. Like we learn this like cool new tool and we tend to discredit everything we used in the past if we find that it has like a bit of this new tool has a bit of an advantage. And I've personally fallen into this trap myself, and at some point I even started to ask myself why functional programming is so cool. Why don't I learn a fully pure functional programming like Haskell? And I feel like a lot of people drift towards that, and we often forget that there's a lot of cool stuff we can do with objects, and that a lot of things in functional programming and on .NET, like with F#, we actually use objects all the time. And we start losing the forest for the trees, and we have these cool tools that we can use, like objects, but we drift away from them just because they're not functional. And this brings me to the point that functional programming, at the end of the day, is a paradigm to help us achieve a goal, and it's not a goal itself. Right, so our goal is, I'm assuming, depending on what project you're working on, you want to deliver high quality software on the external side, so little bugs, good user experience. On the internal side, you want, again, less bugs. You want to make your code testable. You want to be able to automate tests, automate a lot of stuff, and you want to design well so it's maintainable. Those are goals for an end result, for the customer, for whoever's using the software. And the goal is not to be functional, right? If something uses mutation and is 100 times faster than doing it functionally, then it's not functional. No, you just take that new strategy, right? And so that's one important thing to note, that even I fall in the trap. If you listen to my fundamentals tutorial, or even a few other tutorials like writing the simple application, we're not going to look at classes at all. We're just going to go ahead and do it functional, which is fine, if you're learning. But at the end of the day, don't forget all of these other things that work, that you can still make immutable. You can still use them in a functional way, but you're not you're not shooting yourself in the foot, right? So the first point I want to make, or probably the second at this point, is that there's nothing inherently wrong with using classes and objects, right? So there's nothing inherently, you can make classes immutable, you can make everything pure. The instantiation, right? Instantiation of a class, having an instance rather than a static class like a module, there's nothing inherently wrong with that, right? But the problem is, or the thing we want to move away from, is object-oriented programming. So there's a difference between using objects and following a object-oriented paradigm. So these kind of drives, we can look over to it. There's a first off the top of my head, which is the first one I would define is the mutation of state, having some state that is mutated. Generally, we don't want that. Generally, we want to focus on pure functions for testability purposes. So that's encapsulation of data and behavior is generally not what we want with functional programming for good reasons. Also, the idea of using objects as a baseline for interfaces and objects for the baseline of abstraction and implementation is kind of overkill from a functional programming standpoint. We can use functions and function signatures most of the time to abstract the behavior that we want, so the resultant behavior. It's definitely a knee-jerk reaction we normally have writing C#, where you're I have to write this function. Okay, well, I have to write an interface with that method. Then I have to use write a class that inherits from that interface and has one function in it. It's kind of overkill. You can just write that function, and if you need to abstract it or to make it testable, you just say, hey, this is a function that takes this to that, and that'll be easily mocked. You can easily do everything you need with that. So that's the thing we want to run away from. And lastly, just nulls, null references, just mutation of references, all that stuff is something we want to avoid. It's something that we're moving away from with F# and functional programming. So there's also things that we're missing out when we don't use objects. So for instance, even though in F# we can use partial application for dependency injection, doesn't mean like classes are still like really good to inject dependencies, like taking dependencies in interface, having members. So like, let's say you have a function that retrieves user from a user ID. Like having to pass like as a first parameter of that function the database all the time is like very annoying, and you can just use classes for injecting your dependencies. And as this gets much more important if your function starts to have like more and more parameters, right? So if you have like a 7-parameter function, and like 5 of those are partially applied, it's kind of messy. You can just have the class that has a lot of parameters in its constructor, and it's cleaner. Now, obviously, there's other strategies in functional programming for dependency injection, like using reader mode add or something like that. And so I don't want to say that you should always use classes for dependency injection, or you should always use partial application. Like at the end of the day, all of these options are tools in the toolbox, and each tool will be good for each of its situations. So that's one thing to keep in mind. So the other thing we're missing with not using objects is how well they integrate well with interfaces. So in .NET, like if you have public APIs that are going to be shared across DLLs, and maybe you're going to integrate with C#, or maybe you're going to use it's basically either C# or F#. Let's be honest, on .NET. Still, if it's a public API, then a good practice, like in the Microsoft coding guidelines, is to use interfaces for those APIs, because functions like F# functions don't integrate that well with with C#. So it's generally a good idea to use interfaces, and to be honest, interfaces are pretty good to work with in F#. Like we have object expressions where you can just implement interfaces on the go. You don't have to write classes, but that's an object. Like, let's not kid ourselves in trying to like mental gymnastics our way to like we're only using functions. We're actually using objects all the time. So why not and why are we throwing away classes? Like classes are still a decent tool in the toolbox. There's a way, like we're definitely not using classes the same way that we're going to be using in object-oriented programming, but doesn't mean they're not useful. And lastly, some data types that are very mutable, like we should encapsulate them into classes for reasons like thread safety, or they're not good. Like we shouldn't have them static in a module, right? So like connections to databases and stuff like that, you're not going to have that statically laying around. Like encapsulation data, yes, that's definitely something you want to avoid, like especially if the data is immutable, right? But the data is not immutable, it's impure and stuff, then we can work with classes to like hide that mutability and have like a more pure contract, even though it's not pure at all. It's not deterministic, where you don't have to worry about some of the details of that object, right? So that's a tool. Again, it's a tool in the toolbox. Use it sparingly, but that doesn't mean that you shouldn't use it. Like this video is more concerned about how we can use classes to still be functional, right? So most of the time we want to use functions and function signatures, but when integrating, like I said, with interfaces or in other situations, objects are not bad. Like they're not bad. Object programming is fine. We just want to eliminate the object-oriented and focusing too much on the objects. So what types of objects can we create in F#? Well, since we're on .NET, like all the record types, the discriminated unions, the tuples, all of these are reference types, right? You can have them in value types with structs. You can, like, each of those can be structs. But at the end of the day, on .NET, they're all implemented as classes. So let's not forget that. Even though, like, you probably want to use record types more than you want to use class types. Like, class types are more of a last resort, I feel, in certain situations, especially with interfaces. Like, using record types to contain, like, methods and stuff, like, replacing replacing interfaces with record types, I feel, is not very idiomatic in F sharp. It doesn't integrate well with C sharp, and so generally something I want to avoid. Now, in this video, I'm going to mostly be talking about class types. So the classic class types with a constructor, and you have members and stuff, which can also be structs. So they can be reference types or value types, and object expressions, which are really cool. Like most of the time when working in interfaces, that's like classes are like the last resort. If you're using interfaces like object expressions, if it's quick and on the go, it's a pretty cool way to do things. Very lightweight. You don't have to define anything. You still have like that anonymity. If you don't want anonymity, or you want to inherit multiple interfaces, you can inherit multiple interfaces of object expressions as well. But in some situations, you want to use classes. So, and the reason I'm actually making this video is because next video we're going to be looking at computation expressions, which are class types. So I just don't want to get people mixed up. Like normally I wouldn't really have to make this video now, but computation expressions are class types. So just getting a hold of the syntax and how things work is going to be important. Most of the time, still stick to functions, still stick to functional programming, but don't be afraid of the object. Is kind of the message of this video. So we're going to look at the basics of classes. There's just syntax, general stuff you need to know, working with interfaces, a few examples, and that'll be it for this video. So if you made it this far, make sure to leave a like, really helps me out, and we're going to jump on the computer for the tutorial. Alright, let's look at classes. So basically the program for this portion will be to look over general definitions, considerations, things to know when working with classes. Is going to be very basic, just because we don't really want to go too much in depth into classes anyways in F sharp, but you can always go more into depth. So a basic definition, what will that look like? Well, it'll be very simple. You can have type some class. This the simplest we can make a class is going to be this. So the first thing you'll notice is we have the type just like a record type, which is a record type. If we go some record, and let's say it has one sec, just checking my keyboard. Okay, age int. So the first thing you'll notice is the class type has parentheses here. This is for constructor. It has to have a constructor, and that's kind of the notation that F sharp uses. So that's the first difference. And then class end, obviously this is just because I have an empty class. If I were to add a method to it, methods are called members in classes. So you can go member. If I just want to add two numbers together, I can go this.add x, y equals to x plus y. Okay, now let's go a bit slowly here and see what we just saw. So first thing, the keyword member is to designate a member in the class. So members are functions or properties that we want to expose and make public. So members are public by default. We can put the private here to make it private, but that's generally not what we're going to do with members, and I'll explain why in a little bit. Member this.add. So why is it this.add? Firstly, I can put whatever I want here. It can be a bluebee, whatever. This is you declare a variable that will contain the reference to its class. So this is I put this for a reason, because normally in C sharp, this keyword is the keyword of the reference of this this instance, right? Because this member is non-static. So if it's non-static, that means it is a method on an instance. So if you want to refer that instance, this is one of two ways you can do it. So you can use this keyword here, or the other thing you can do, you can have a self-identifier here and call it self. So I will have to remove this. And basically, this and self is basically the same thing here. So there's a reason why you can do this notation, this self-identification, and I guess we'll go into that
right now, because you can have let bindings in classes. So let binding, we can do let minus x y is equal to x minus y. Okay, so it can declare functions and values in here. So let um, 10 equals 10 or whatever. We can do that. And let bindings are private. Even if I try to add public here, it's going to say, hey, let bindings will always be private or must be private. Multiple visibility attributes have been specified because by default let is a private binding in classes. So that's just one thing. If it's private, use let. If it's public, use member. That's basically one thing to keep in mind. And we can have many of these, so that's pretty cool. Let's talk about parameters. We can have curried members, like with normal F# methods. So we can have a curried method notation. But let's say I want to write another member here. This dot add, and let's keep our 10 here. Let 10 equals 10 for some reason. And we want to add x plus 10. Let's say I want to do that. Well, this does not work because now we have an overload and curried members cannot overload, basically. In C#, you can overload how you want uh, with different parameters, and C# methods are not curried by default. And so if we want to overload this method, we can definitely do that, but we have to use tuples. So this compiles. This is actually the only way you can do method overloading in F# is by using tuples. Well, it's tuple. I guess it's a tuple in F#, but in C#, it's basically passing parameters with a comma separated list in parentheses. Yeah, I guess it's a tuple. I guess you could call it like that. So that's one thing to keep in mind. Secondly, just like in F#, we can add type annotations here. So if I want to add doubles, we can definitely do that. And double will return a double. And one thing to keep in mind as well, a very big downside with classes is they do not support statically resolved type parameters like normal F# functs do. Let me remind you that in F# you can't actually add doubles to ints just because of the strong typing, so you'd have to basically convert them to doubles. Even if you use the inline notation, so what inline does is it allows you to basically use statically resolved type parameters. And so in order to add two floats together, or basically if I don't have this inline keyword, this will resolve itself into an int to int function. So these two parameters will be automatically resolved to ints. If I want to make it generic, I have to use the inline keyword, which will basically apply the statically resolved type parameters that this function has defined, that the plus function has defined. And in class types, the support for this is very limited. So that's one thing to keep in mind. We can use generics, like normal generics that are resolved at runtime. Now, just like in C#, class types can have properties. So properties are fields with getters and setters, or only getters or only setters. So basically, there are values that can be accessed or set from the external world. Generally, it's not going to be very idiomatic to use, but if we want to have a get only setter, just member. And basically, when we're not using this keyword, we can just go over here and do an underscore just to remove the confusion that we're not actually using it. So member 10 is equal to 10. So basically what I'm doing here is I'm exposing this private value that I have. and I'm bringing it here. Actually, I could just, in theory, just do this, since, and now this one wanted 10, so we can do self.10 here, if you don't want it to do that. That's one thing you can do, and if you want to redefine the getters and setters, you can go member 10 here with get. So get is you're going to pass unit, and it's going to it's going to return a value. So that's redefining a get only property with the get syntax here. And if you want to set the setter, we can just come and set. You have to pass it a value that is of the same type of the return type of the get. So basically, the return type of get and the parameter type of set need to be the same. And the parameter of get is going to be unit, and the return type of set is going to be unit as well. So if I come here and do value int is equal to, and then I could just, print f the value here if I wanted to. Obviously, this makes no sense. I'm just going over the syntax, just so you can know you can do it. You can use these tools, but if you're going to use like properties most of the time, it's going to be used as you're going to use record types anyways. I'm just going over a bit of the basic syntax here. And so in practice, what I'll do is if I come here and I instantiate some class, so that's one thing we should have talked about, how to instantiate a class. If I want to go here, some class is equal to some class with the parentheses. So that will instantiate me a some class type if I select everything and go to the executable or the interactive. So I have some class is some class. And one thing you'll note is there's no new keyword here. So the new keyword is actually redundant. We don't have to use it. The only exception to that is if we're using classes that inherit from iDisposable, it's a good practice to put new to signify that it's disposable. That's a common practice in field. Even the compiler will let you know. And in those cases, if it's enumerable, you're actually going to use the use keyword. But in this case, obviously our class does not inherit from iDisposable. So, and use basically we'll call dispose at the end of its scope. So that's pretty cool as well if you didn't know that. All right, and if I come here and I do some class dot 10, what that will give me is it's 10. And if I set, so if I set 10, I do 3, for example. Whoop. So when I did 10, it returns it equals 10. Then when I set it to 3, there's a 3 here that's really random. It's just because it's not, it's printf. I didn't do printfn. There you go. And now it is unit. That's just how it works. And obviously we can go and do the add method. So I do some class dot add, and then I just do 20. This will add, like we did here, x plus self 10. So that's 10 plus 20 is 30. And if I do the other add call, some class dot add, now I have to return a tuple, so I do 5 and 15. And it's telling me, oh, I said I needed doubles. Here, I'll just do int like this. And this should compile now. Oh, I actually have to redo this. Resend it to interactive because the definition changed. And then, oh, okay, I'll just rerun everything to be honest. There you go. So 5 plus 15 is equal to 20. So that's a basic just members, and members can be static as well. So in this case, I can just add static here, and since it's static, the syntax changes a bit. It doesn't have the self reference, before the member name. So I'm gonna just remove that, and instead of calling on my instance, I can just go ahead and do some class, so the name of the class itself. And if I run everything, I have it equals 20. Or if I just change it just to make sure it works, it equals 21. All right, let's talk about constructors. So here with these parentheses, we can actually add constructor arguments here. So if I do first and second, these are actually two constructor parameters, and I can actually come here and change this definition for add. So I can do first plus second. Oh, and since we have to remove the static, of course, and we have to add the self-reference, okay. So this takes unit and returns an int because with the type inference, it resolved that these two are ints. So by default, the plus will think that it's an int. So that's one thing. We can also, of course, do type annotations here, so we can set these to doubles. Okay, so now it's unit to double. And let's say we wanted to add a default constructor. Well, one thing we can do is we can actually go ahead and define that with the new keyword. So new, and it takes unit. Now this function has to return a sum class, right? So we can just do sum class, and by default it's going to be 0 and 0. We could also, for example, have a third constructor. So this is one constructor, this is another constructor, and we can also add a third one. Let's say if we only want to specify the second argument. So we can do first is equal to sum class, and I can automatically give this first that we're passing in here, and go 0 by default. So now we've defined three constructors. So we have the one by default, which takes all the arguments, because this one basically has to list all the arguments. And so sometimes you just want to create a class and only have arguments by default. So this is why these redundant constructors are really cool. And notice the difference with other languages, where you can have constructors that basically constructors don't necessarily return an instance of the class. Let's say in C#, constructors will like set the fields, and yes, you can call other constructors with the like two dots, this parentheses expression, or even the base class. But this is very concrete that you're always returning something, so that's kind of interesting, an interesting change. So if I come down and I want to instantiate this sum class, I can do no arguments, and if I want to use the new function, which takes unit, so if we go back here, this function will take first and second. It's a bit confusing how I did it, which like this one takes one parameter and adds 10. This one adds. I'll just remove this one because it'll be confusing for now, and I'll remove the 10 here. It's kind of confusing. So we can go ahead here. Now if I execute everything, we get 0, 0 because by default, if we don't pass any items in the constructor, it will return 0. And if I pass 5 here, and I do this, so it's equal to 5, and if I pass two numbers, it'll add them together. So 5 plus 7 should give us 12. Alright, there we go. So you see how I now have three ways I can construct this class. We can actually have a do command. Now, a do command is something that will be executed after construction. And so I'll add some logs here. If I just want to do print fn, and then go constructing with, and I could go, actually probably can use string interpolation here. And I'm gonna go and preface this with do. I will preface this. I actually can't do the same printout here, and I'll explain why. It's actually simple. So here, I don't have access to first and second. And this is because, obviously, in this, well, maybe not obviously, but here, I'm constructing with 0 arguments, and my instance is actually being created here. So I don't have access to these fields because I'm passing them here. New with no parameters. Here you can do first. Okay, so now that we have our printouts here, so we have in new first, and do. Let's go over here, and now we have this. We already passed 2 parameters, so in theory we should only have this printout because we're not actually going into these constructors, since we're passing 2 parameters. So we're not passing no parameters. We're not passing 1 parameter. We're just going direct here. So if I execute this, it says do constructing with 5 and 7, so that's exactly what we want. If I just remove 1 term here, so the first printout is in new first, so this is this constructor. That's just exactly what we're expecting. Constructing with 5 and 0, so it goes into here. Once this is instantiated, then it executes the do commands up here, and then it will do the rest, which is nothing in this case. So that's what we're expecting, and then if we have no printouts, constructor with 0 and 0 in new here. So that's what we're expecting. So that basically just lays out in what order the constructors are executing. Let's move on to interfaces. Interfaces are pretty important to decouple our implementations with our abstractions, especially when working with interoperating with C#. It's pretty important. And even if you're not, it's just good practice to regroup many abstractions in one interface and use that. So we are going to go ahead and look over the definition. So if you want to define an interface, go type I add, let's say. And if you want to add a method here, so that define a method or define a method in the interface, you're going to use abstract member add, and then in this case, maybe let's use this member, the method we want to add to the interface, so we can do unit to double. So we're not adding the implementation, we are only adding the type signature. So abstract member add, the name of the method, and then we go ahead and define what's the method signature. One thing to keep in mind with interfaces and how to implement interfaces is that in F#, so in C#, normally you can define interfaces implicitly, which just means, let's say you come here, you do 2 dots and do I add. And then if you already have a member add here, then you simply, it's simply done, everything compiles. In F#, you have to explicitly define, implement the interface, which means under everything, you come here and do interface I add with, and then you have to define the members explicitly. So you have to make sure everything is defined correctly. You can't, it won't automatically just say, hey, okay, you have an add method, you're good to go. So here you can generate missing members, and if I want, I can just do, this dot add. I don't actually know what the decision was on that, to be honest. Very honest, I don't know what the pros and cons to that. It seems kind of a downside to not be able to implicitly define it, but I don't know the reasoning, so I can't really judge at this point in time. Another way to implement interfaces is with the object expressions. So object expressions are a really cool way to basically define implementations of interfaces on the fly, like anonymously, if you will. So you can do a new I add with And you can go ahead and implement the members. So member this dot add unit is equal to, well, in this case it would be kind of nonsense to implement this interface, but you can go like 7 or something. And it doesn't make sense because it will only make sense in this case to have the numbers injected in the constructor or some reason. So this is kind of a nonsense implementation, but just to get the syntax here, new interface with, and then you define the members. So if this had another method called minus, see, it says here that it's missing an implementation. So we're missing I add minus. So if I copy here, this works. And if I wanted to add another interface to it, so I woof, for some reason, I don't know, member woof, and it'll be unit to unit, just to print out, to be honest. And if I want to implement another interface here, I can go where the new is and do interface I woof with, oh, because there's a typo, interface with member, what's it called, woof, or this dot woof. Do that, and you can do prints if you want. Print fn woof. Alright. So you can add multiple interfaces in an object, and then this is actually pretty cool, like for testing purposes. So, sum object is equal to. Now this sum object is an I add, it's also an I woof. And the downside is that I would have to cast it as an I woof if I wanted to use this method, because it's not, you see here it's an I add. So if I do sum object dot, so I have add and minus, but I don't have woof, so I have to cast it as that. So I have to go I woof, and it's kind of a side cast, so I have to do it like this. So if I come here and do all of this, I also have to redo all these interfaces. Okay, good. Now it is an iWolf, so this is a wolf object. And then come here and do dot wolf, and it prints wolf here. And of course I can just use this interface here, I add. So if I do sum object, I can do add, it's supposed to give me 7, and the minus, let's just do 9. I should really come up with better examples, make it more entertaining, to be honest. But and I have to redo this. 9, okay. So hopefully I didn't bore you too much with the woofs and the 9s and the plus and minus. I know it's not the most entertaining examples, but yeah, just to get the syntax down, just to know it's possible and move on to cooler stuff. So we went over basic syntax of classes, basic syntax of interfaces, object expressions. I'm going to conclude with just a brief segment on when you should use what type. It's hard to know sometimes when to use record types or the discriminated unions, classes, tuples. And so briefly, I want to communicate that a class is basically a last resort or an option to use when interoperating most of the time. If you just want to contain data and aggregates of data, record types are like the premium way to do it. For data modeling purposes in F#, discriminated unions I feel are far superior than using interfaces and composition with classes. So that's one of the things to keep in mind. To model your domain inside your F# software, prefer discriminated unions as opposed to interfaces and composition and stuff with classes. That's definitely for sure. I also wanted to briefly talk about structs versus classes. So on .NET, you can have structs, which are value types. So normally classes are reference types, and what that means is when you're passing an object to a function or to a class or to someone else, you're either passing its address in memory, which is the reference. So you're either passing that, and normally that's the size of the address what they use. Normally it's an int, so that's 4 bytes. Or you are passing the whole object itself. So in the case of double, you're not passing something in memory. You're passing it as you're copying the value of that to that function, and so that's a trade-off you have to consider if your class is very small. So in this case, I have 2 doubles. So a double in memory is 8 bytes. So I have 2 of them. So that's 16 bytes of data. Makes sense to have this as a struct. So what that will do is it will make it so if I have another function that takes a sum class, which probably the name is bad because I'm using it as a struct, so it wouldn't be sum class. But anyways, if I'm passing it to a function, or I'm passing it to another method call, as a struct, it's going to pass the data, the data of the object itself instead of its reference. So that's passing by value instead of passing by reference. So normally you're always passing by reference, but with structs you're passing by value. And so you only want to do that when the data, the size of the object is small. In this case, it's small, so it's good to go. And if you have a bigger object that contains a dictionary or anything above 16 bytes is what Microsoft mentions on their documentation, you mostly want to keep it by reference to have good performance. Also, something that's going to allocate very often is something you can gain a lot more with some classes or with struct types. As you saw, I deleted some stuff because some things are not permitted with structs, so you can't have do bindings with structs, and you can't have default constructors with structs. So that's just one thing to keep in mind. And yeah, that's basically what I wanted to mention with this tutorial. So I know the pace of it was a bit slow. I'm a bit tired trying to crank out this tutorial. Hopefully you know how to use classes now, and you shouldn't really use them very too often, but we're going to look at computation expressions next, and I want to make sure that people had just some idea of the syntax we're going to use with computation expressions of how to build them, and so that's why I expedited this tutorial instead of continuing with my computation expressions. And so hopefully you enjoyed it, and I'll send it to the outro now.
Alright, so I hope you enjoyed that. Hopefully you just get a little bit of an idea of classes and how they kind of integrate with the F# functional programming paradigm. If you enjoyed this video, leave a like, comment for feedback and suggestions and stuff, or if you liked it. And subscribe for more videos. So videos we're going to be looking at computation expressions and asynchronous programming next. So stay tuned for that. If you need any consulting or development services in F#, I offer freelance F# development consulting. So you can check out my website below. In any case, I'll see you in the next video. Peace.